he has to solve this equation. Okay, so x is something like eccentric anomaly. Okay, so of an object, like in the sky, you can have many stars that go in an elliptical orbits, and then those parameters is like very important in determining the orbit of that celestial body. So the equation is like x minus a sine x equal b, and you see that there is no formula, no direct formula for you to solve this. And some other time you can have an equations. What is a system of equations? Okay, so nonlinear equations, and your unknown can be a tuple of n numbers. So you have to find the the solution so that f of x equals 0. Yeah. And another example is, well, a system of equation could look like this. Okay, so you have like 3 nonlinear equations, and you have to solve for x, y, and z. And you see, like, you don't have any method to solve this one explicitly, right? And now something is more relevant to your real life situation is the navigation equations. So watch this one and I will explain a bit more. Well, essentially it's GPS, yeah. So you can watch the rest of the video by clicking the link here. But anyway, so what is behind GPS? So essentially, you have 24 satellites on the sky, yeah. And in order to determine your location, say your mobile phone, yeah, every mobile phone now have a GPS receiver. Then you need only 4 satellite signals. You need signals from 4 satellites. Okay? So your phone will receive the position of those satellites plus the time they send you the signals. Okay? And then you have 4 unknowns. So what is the 4 unknowns? So first is 3 coordinates, x, y, and z, your current coordinates. Okay? and then the delay of your clock. Yeah, so your every clock on each mobile phone has a different delay. Okay, so let me draw pictures to explain those equations. So suppose you have four satellites, yeah? So this one is 4 satellites on the sky. Okay? And this is you. Or maybe me, yeah? Doesn't matter. So with a mobile phone, yeah? And the mobile phone has a GPS receiver, okay? Okay? So then, I will receive the signals from 4 satellites. So the signals will contain, the coordinates of the satellite and the timestamp that send you the signals. Okay? So this one X1, Y1, Z1, and the last one is X4, Y4, Z4, T4. Okay? So it sends you just have 4 signals. And now we have the distance, yeah? So suppose I put the distance. So this one, suppose my position is given by X, Y, and Z. So unknowns, yeah? So X, Y, and Z unknowns. Right? So then I have the distance from here to here. Okay? So by a Pythagoras theorem, then the distance will be x minus x1 square plus y minus y1 square plus z minus z1 square, right? Take the square root. Yeah, so this is the distance between the satellite and me. Yeah. And, sorry. Let me just forget the microphone. Okay, so then what happened is the distance, okay, can be computed by the time multiplied by the velocity of the signals. Okay, so it can be computed by the time. So what is the time? So the time will be the time I receive the signals. Yeah. So what is dr is the time I receive the signals plus some delay from my clock minus t1. Okay. So you see, this is my current time. And T1 is the time, the satellite send you the location signals. Multiply by the speed. Question? Huh? Multiply by the speed. So what is the speed of the signals? C. Huh? C, yeah? The speed of light, yeah? The speed of light is known. So electromagnetic waves travel at the speed of light. So you see, then you have this equation. So what is essentially this equation? Yeah, so C is the speed of light, yeah, and dr is the time I receive the signals. So you see, you have 4 equations because you have 4 satellites. And then why do I need 4 equations? Because I have 4 unknowns. I have X, Y, and Z, yeah, the coordinates, my local coordinates, and then the clock delay, yeah. So that's why I have 4 equations. And now you have to solve 4 equations to identify your location, okay? And from your location, from the X, Y, and Z, then they will map to the, maybe some Google Maps, and then it will pinpoint directly your location on your screen. Okay, so there is some calculation going behind the scene, and now you just use a mobile phone and you know where you are. It's easy life. So, but behind the scene, they have to do this. Yeah. Okay, so now we go to numerical methods. So now, numerical methods. So the first method is bisection method. So bisection method is summarized in 3 steps like this. Okay. But those 3 steps can be illustrated by pictures. So now suppose I have, so go back to the equation, only one equation, yeah? So suppose I have only one equation like this. So f of x, and I want to find x star, so that f of x star equals 0. Okay? And now I assume that the function is very nice, it's continuous. Yeah? More than that, I assume that, I know the solution is somewhere in this intervals. Okay, a-n, b-n. Okay, so maybe start with a0, b0, yeah? So make it. So maybe my equation look like this. Yeah? So this is the x star. So I'm looking for x star. Okay? And now I'm looking by, initially I have the intervals a0, b0, right? I just chop it in half. Chop it in half here. And then I define this one to be x1. So x1 is my a0 plus b0 divided by 2. Okay? And now, I will check 2 intervals. I will check a0, x1, okay, and x1, b0 to see which one is the intervals that I should zoom in. Yeah? And you see that the intervals x1 and b0, because the signs are positive, right? Because, the function above the OX line, so I have to skip this one, yeah? Then I choose the second one. So now the interval a0, x1, I check the signs, yeah? So I have opposite signs, okay? So then I define this one to be my a1, and this one is my b1, yeah? And similarly, now I compute x1, sorry, I compute x2, yeah, because now x1, oh sorry, this one should be x0, because according to this formula, xn, so this one should be x0, yeah. So now I compute x1, so x1 will be, somewhere here. So x1 will be my a1 plus b1 divided by 2, yeah. Then I will check 2 intervals. And you see that these intervals, a1, x1 is not good because the signs are both negative. So I have to choose the intervals in the middle. So now this one will be my a2, b2. And then I compute, x2 will be the middle point again and again. So you see that according to this process, the interval just get smaller and smaller, right? It got shrunk by a half every iteration, yeah? And more than that, it just got zoomed in. It just got zoomed in the closer and closer to the solution of the function. Okay? So that is exactly how it is written here. So step 1 is you have to find the interval so that they have opposite signs, yeah? You find the midpoint, and then so you have to choose which half you go further. Okay? And if you cannot do that, then it means that the function is 0 and then you stop. That is a solution. Okay? And it's called bisection method because every time you divide it in two halves. So you see, I mean, you just repeat this one, you know, again and again until you have some conversion. So why does the bisection method work? Why it works? Intermediate value theorem. Okay. So mean value theorem say that, you know, this intermediate value theorem is the correct one. So intermediate value theorem. So intermediate value theorem say that if the function is continuous, yeah, on the intervals a and b, yeah, so continuous is important, and fa and fb are opposite signs, okay, then there is a zero. So there's a zero in AB, so that fx star equals 0. So this one is intermediate value theorem. And you see, it's very important that the function has to be continuous. Otherwise, you cannot use this method. Okay? And what is the conversion rate? Well, you can see that every time, you know, I mean, you reduce the width of the intervals by half. Yeah? So the conversion rate will be, you know, an, I mean, the conversion rate will be bn minus an, and so maybe you should write here. Yeah? So you see that bn minus an will be 1/2 of bn minus 1 minus an minus 1, yeah, is 1/4 of bn minus 2 minus an minus 2, and so on, yeah. So up to the last one, so 2 to the n, then you have b0 minus a0. So the conversion rate will be about 1/2 to the n. Yeah, n is the number of iteration. So this one is how you implement it in MATLAB. So you can implement so like this. So suppose I want to solve x minus cosine of x equals 0. Then I define f as anonymous function. Okay, so anonymous function can be defined this way. And then I just implement the algorithm. So first I choose the midpoint. So midpoint is just 1/2, the left and the right, yeah. And you see, like, we never have the case f equals 0 exactly, because there's still epsilon, you know, like you approximate the real number by numbers, floating point numbers, so therefore you know, you cannot make it equal 0. Just make it less than epsilon is good enough. Less than epsilon is less than 2.2 10 to the minus 16. Then it is a 0. Otherwise, you have to check which intervals you want to go further. Okay, so if I consider the left, and if it's a different sign, then I choose b to be xn. Okay, and if, you know, I mean the right intervals has different sign, then I just choose a to be xn. So you see, I don't want to store an and bn because they are redundant. I just reuse it. I just reuse the variable a and b again and again. Okay, so that is how we implement it in MATLAB, and you can see how it works. So this one is I just wrote it before, yeah. So bn minus an is just 2 to the 1/2 to the n, b0 minus a0. So see, you can see how it works here. So this is exactly here, yeah. So, and we run it. So 0 is this number, okay? And you can check that if you put in f of x. Now we have xn, yeah. So f of xn. So xn is 0. See, very good, yeah. So xn is this number. Solve the equation. So now we talk about the second method, which is a fixed point iteration. So fixed point iteration is slightly different, but I mean the algorithm is simple as well. So suppose you have a function. So in our case, like the equation is x equal e to the minus x, yeah. Then what happens is you just define x1 to be the function at x0, and then x2 is the function at x1, and so on. Okay? Then you will see that at some point in time, then it will stable. Okay? So now, suppose I just plot it. So this one is the line y equal x. Okay? And the green one is y equal e to the minus x. Yeah, so the 0 has to be here, yeah? So initially you start at 0.5, okay? Then you project it to the function y equal minus x to get x1. Yeah, so you project it to the function and then you have to flip it over y equal x to get x1. Yeah, so the second dot is x1. You do the same, you got x2, and so on. You see, so it go through a spiral, and eventually it will converge. Yeah, so that is how geometrically it looks like. So eventually, you go to the solution here, and now you can implement it easily. So now suppose I start with x equals 0.5, and I just run like 15 iterations. So every time I just reuse the variable x again. So x is just equal f of x again and again, and you can see that it will stable out like this. Yeah. But now suppose you change the equation a bit, yeah. So now, let's see. I think I have a Google form here. So fixed point iteration here. So now suppose I change then now you can see it now. Suppose I change the equation to x equal e to the, so before e to the x, yeah, before e to the minus x, but now if I change it to x equal e to the x, then you apply, the same algorithm. Then what happens? So does it converge to a solution or does it close up? So either you make a guess or you do some calculation, okay? You just plug in your calculation, plug in MATLAB or calculator and, see whether you have the convergent solution or not. So try it, just try it, because it's a fixed point iteration method, so try it. So let's see whether anyone have tried it. See, because you have to try it to see it. So fixed point iteration. Oh, 9 people already, very fast. So, but we don't have a majority. So there should be a majority. And now this one is like split into half. It's like election. I mean, this one is something like you can test easily. You know, I mean, you don't have to make a guess. Just plug in calculator, plug in MATLAB, plug in your mobile phone, plug in anything. You know, at least you see how the method works. Okay? Cannot be 50-50. If something can be verified easily. Okay? So maybe let me verify for you, okay? So now suppose I just change this. So fixed point, yeah, fixed. Okay, so you see, that is your equation, right? And then now I just run it. And you can see that after 5 iterations, it becomes infinity already. You see? So you can use your calculator, just pocket calculator. You can check it. You plug it in. You know, you got x, e to the x, and e to the x. So you see, so what is going on here? So the fixed point iteration, you know, sometimes it works, sometimes it just blows up. So that's the main method. It's not like the bisection. Bisection, okay, I mean, by intermediate value theorem, you always find a solution, okay? But in this case, you know, like you change the equation, then it blows up. See, now if I put minus x, I run it, and it's stable, 0.56, right? And, you know, I change it to plus x, then it just become infinity. So there is some condition, you know, have to be met before you can use this method. And now that is the next slide, yeah? So before we look into the condition, let's look at the general form of the method. So the general form of the method is x equals g of x, right? And this is the general form of the equation. And you want to find x star. So that x star equals g of x star. Yeah, so that is the procedure. And the algorithm is you just define xn plus 1 to be g of xn. Yeah? And now, yeah, like I said, the solution is x star when gx star equals x star. Okay? And now, how do I know that the method will converge? So how do I know this process will converge? How do I know that this method will converge?
You have to be like a contraction. No?
Yeah, you get the idea, yeah? But we have to make it more precise, yeah? Essentially, yes, what you want is this one has to be a contraction, yeah? But in order to make it precise, well, actually, we did this one already, yeah? So we have to define the errors, okay? So the errors will be the difference between your approximate solution and the exact solution. And you want these errors to go down to 0. Okay? And now, you know, you can compute that the errors at time step n plus 1. Okay? It just equal xn plus 1 minus x star by this definition. But xn plus 1 is just g of xn. Yeah, that is how you define the iteration, the fixed point iteration. And g of x star equal x star because that is a solution. Okay. And then, you know, you have xn is just x star plus en, then minus g star. And now what is the next step? So like you said, we have to show that's a contraction. But what does it mean by contraction in terms of the errors? So what is the next step? You take what?
You take the ratio of E of the n plus 1 error over the n error. Is equal to
Yes, but then if you take the ratio, then how do you get this one cancel? What you say is correct, but we have to do one more step before you take the ratio. Well, what you said is you take the ratio numerically. Yeah, that is okay, but now we're just doing theoretically. So how do we show that en plus 1 has to go down when n go to infinity? Huh? So what step you need to see? The idea is you need to relate en plus 1 with en. Yeah? So like you said, you take en plus 1 divided by en. But if we divide it here, then we don't have anything yet. Before we do that, we have to process this term a little bit.
absolute value. Current expression.
Yeah, take absolute value, yes. And then one more step, one key step. So now what I want is I want to get out en from this right-hand side. Taylor expansion, yeah. Okay, either Taylor expansion or mean value theorem. So either way is okay. Okay, so if you take mean value theorem, then you got G prime and you got En. Yeah? And you got Taylor expansion, the same. Okay? So then you get out, this one is G prime En. Yeah? And you ignore the higher order term. So essentially, you see this is a relation between En plus 1 and En. En plus 1 is approximately just G prime x star times En. And now back to your comment, you want it to be a contraction, yeah? So then what condition you want to make this one a contraction?
Must be less than 1.
Sorry?
Less than 1.
Yeah, G prime in absolute value has to be less than 1. Okay? So if you want these errors go down to 0 when n go to infinity, then G prime at x star in absolute value has to be less than 1. Okay, otherwise the errors blows up. Yeah? So we expect conversion if G prime x star less than 1. And you can see that for G equal e to the minus x, when you take, like derivative, then you got e to the minus x, there's a minus, but take absolute value. But still, if x is big enough, then it's less than 1. Yeah? But e to the positive power of x, when you put x big, it could be bigger than 1, blows up. Okay, so that is why, the first method, the first example converges to a solution, but the second is not. Yeah? So, unless, G prime is very small, then the conversion is slow. Then you have to use other methods. So this one is, like another example. So now you have x equal g of x, but g of x is 1 over hyperbolic cosine of x. Okay? And you see that when you put g equal 1 over hyperbolic cosine, you take g prime, and you put in x star, then it will be less than 1 in absolute value. Okay, and then you can see that the error is going down. Going down, but you see, even it's going down, but the error is still like 10 to the minus 4, yeah? Okay, so that is like two methods, two first simple methods. And now the next method will be Newton method. So Newton method. Well, so before Newton method, let me ask you one question, yeah? So So Newton method is a method proposed by Newton, yeah. So Newton, he wrote many things, so he invented many things. But let me ask you one simple calculation, okay? So you have to do it, otherwise you will fall asleep, okay? So now, suppose you draw a curve, simple curve, yeah? So f of x is x squared minus 2, yeah? Then you draw a tangent line at x equals 2 to the curve. Then you find the intersection of the tangent line and the x-axis, okay? So it could be those 5 choices, you know, 1.4141, which is about square root 2, yeah? So about this one a bit bigger, 1.5, a bit bigger than 1.5, 1.6. Okay, so now draw a curve and draw a line, okay? And then see what is the correct results. So go back to the another form. So let's see Newton method. Okay, so this is my Newton method. So one response, 1.5. So 3 responses. So I'm still looking for majority, okay? So now let me draw pictures. So it's very easy if you can study mathematics like in a democratic way like this, you know. But in many times, mathematics has only one solution, okay? So it cannot be like this, you know. So you have a curve, yeah, x squared minus 2. So x squared minus 2 is like this. So x squared minus 2, yeah? And then at x equals 2. So now, what is this one? So x squared minus 2 equals 0 here. So plus square root 2 minus square root 2 here, right? Yeah? And then I draw a tangent line at x equals 2. So this one 1.4, so maybe 2 is here. So this one is x equals 2, yeah? Then I draw a tangent line. Okay? Then what is this point? So definitely it's not equal square root 2, right? It has to be somewhere bigger. And so if you say that is, well, it could be, so when you draw pictures, it's not easy to say, right? It could be any of those 4 or 5 numbers, yeah? So we have to do some calculation, okay? And so now if you do the calculation, so what is the equation of the line? So the equation of the line will be y minus f of x0 equal f prime x0 x minus x0, right? Yeah? So in our case, x0 just equal 2. So I just have y equal f of 2 plus f prime of 2 x minus 2, right? Yeah? And now my f is, so this one is f, yeah? So this one is f of x. So my f of 2 is just 4 minus 2, which is equal to 2, right? And f prime is just 2x. So 2x is just, so this one become 4, x minus 2, right? So what is just 4x minus 4. Yeah, so this is a tangent line. And now you have to set y equals 0, right? So when you set y equals 0, oh sorry, it's not correct. Yeah, minus 6, yeah. So when you set y equals 0, then you got x equals 6 over 4. What is 3 over 2? It's 1.5. So this point is 1.5. Okay? So then I have how many percent got 1.5? Only 18%. Okay, so the rest is just like for fun, right? I mean, you're not serious. But anyway, so well, you will be serious in the exam anyway. So you see now the Newton method can be described by exactly the same pictures. Okay, so you have a function f here, the red curve, yeah, and then you draw a tangent line, okay, and then the tangent line will cut the OX at xn plus 1, and you just repeat the process, okay, and you see that in the next time, then I get the tangent line that here get down here, then it gets closer and closer to the intersection. Okay, so now, so this is the formula. So how do I get the formula? So go back to these pictures again. So this is just a very concrete example, but now it could be very general. So now suppose the tangent line at xn will be y minus f of xn equal f prime xn x minus xn. Yeah? So this is identical to this equation, right? And then, you know, the equation of the line is just f of xn plus f prime xn x minus xn. Yeah? And this point is just xn plus 1. So you set y equals 0, then you got xn plus 1. So y equals 0, then you got fxn plus f prime xn plus 1 minus xn. And therefore, you have fxn equal f prime xn minus xn plus 1. Okay? And you divide it. You know, so f prime xn here equal xn minus xn plus 1. Or rearrange it, then you have xn plus 1 equal xn minus f of xn over f prime xn. And this is the formula for Newton method. And Newton, he came up with this method when he was about 26. Okay? So about your age, or even, you know, like maybe a few age younger, sorry, a bit older, right? Not younger, but a bit older. About 26, yeah? And he derived everything. He wrote a book when he was 26, book 600 pages. You can find it on the internet, you know, now you can find those pages. Principia Mathematica, you know, and he knows everything. But anyway, so you can view, you know, these pictures at the key pictures of Newton method. You start with the red point here, you find the tangent line, and you draw the tangent line, you cut OX, and it becomes your xn plus 1. And you do it again. You know, you take xn plus 1, you draw a tangent line, cut xn plus 2. Then eventually the sequence go to the 0. Okay? And if you don't like the pictures, then you can go back to the Taylor formula. Okay? So the Taylor formula it looks like this. So Taylor formula, when you expand around xn, yeah, and you drop a high order terms. Okay? And so it's like you have only the linearized version of the equation. Then you set it equal 0. Okay? So essentially this one is just a line, the tangent line at xn. And you set it equal 0, it means that you find the intersection with the OX axis. And then you have the same formula. Either way, it depends. Which one is more convenient for you? You know, you can come from the Taylor formula, or you can come from the pictures. Okay? So now, so this one is the equation for Newton method again. Sorry, the equation we considered before, but now we use Newton method. And you can see that before, yeah, if you remember in the previous slide, well, we can go back to the previous slide, yeah. Yeah, so the same equation, okay? But after 7 iterations, then your errors is about 10 to the minus 4, yeah? But here, after 6 iterations, then the errors, you know, I mean the value of the function become very close to machine errors. So Newton method go to the solution faster than the previous method. Okay? So now, so that's how do we implement Newton method? So first, we have to define the function, yeah? And then define the derivative of the function. So in this case, I just define both in terms of anonymous function. And this is my formula for Newton method. So xn plus 1 is xn minus f of x over f prime of x. Okay, but because I reuse the variable x again and again, so, you know, this equation look like, you know, I mean, it doesn't make sense in terms of mathematics, but it makes sense in terms of computer programming. You know, you just rewrite, you know, the value again and again into the variable x, and eventually x will be your 0. Okay? And we can run it. So Newton so see, I run it, and you see the solution start, I mean the point start from 1, and after 9 iterations, then you get a very, very good solution. So we can view Newton method as a special case of a fixed point iteration, right? Because remember, xn plus 1 equals something on the right-hand side. And the right-hand side can be viewed as a function g. Okay? And then you can see that when you take g prime, yeah, then g prime will equal something like this. And so g prime is always equal 0. Yeah? Because when you put, sorry, g prime at x star is always equal 0. Because when you put x equal x star, then you got fx star here. So fx star equals 0. X star is a solution of the equation, provided that f prime is non-zero at x star. Yeah? So in that sense, then, if you view Newton method like fixed point iteration, then it is very good, the best iteration you can get, because the ratio is always, you know, I mean, this number is always equal 0. Yeah. But actually, you know, in the next lectures on Friday, we can prove that en plus 1 over en squared, okay, will go to a fixed number. Okay, so we discuss the proof next time when you're a little bit less sleepy than today. Yeah? So maybe on Friday, yeah? So we will prove why this is the case. And then why, you know, Newton method is faster than fixed point iteration and the bisection method. Okay, so see you.